Thank you for giving me the opportunity to present at this symposium. I'm Arko Chakrabartiroy, a senior at Stuyvesant High School in New York City. And today I'm going to talk about my paper, Developing Optimized Machine Learning Models for Timely Prediction and Prevention of College Dropout. I'm extremely grateful to my mentor, Morteza Sormati, for mentorship, guidance, encouragement, and many insightful suggestions and discussions that he has given me. College graduates earn substantially more and are more likely to be employed. Because of this, it is critically important to understand the predictors of college dropout so that students and administrators alike can make a difference in college graduation outcomes. Previous studies remain pretty limited in the scope of evaluating machine learning models for dropout prediction. This paper, on the other hand, has an expanded distribution of the related literature and the contribution of this paper. Since this is a short presentation, I will not talk about the literature, but I will talk about the contributions in the next slide. Leveraging a dataset of 4,424 students, I identified the optimal machine learning model for predicting college dropout as a classification problem. My findings highlight the value of using machine learning for timely dropout risk prediction, which allows for targeted resource allocation in order to reduce risk and support successful graduation outcomes. Well, this paper contributes to the literature in several ways. First of all, we consider a broader set of models, specifically 7 models, with different levels of complexities to detect the optimal model for predicting dropout. Second, we consider 6 evaluation metrics, while the existing literature considers many less. Third, we engage in feature optimization by extensively examining what the most important features in predicting dropout are. And fourth, our dataset includes some key features that are not present in existing studies, which include course information and grades, financial information, and comprehensive data on the state of the macroeconomy. All of these things will have important roles in predicting dropout rates. In this paper, we begin with exploratory data analysis. Next, we conduct some feature optimization to choose the optimal set of features to be used in my models. I follow this up with model optimization with grid search and k-fold cross-validation. Next, I conduct model evaluation and study different testing to training ratios. And finally, I compare a multi-class classification approach to a binary classification approach. This paper uses a comprehensive data set of 4,424 students, like I mentioned before, enrolled in an undergraduate degree course in a post-secondary education institution. For each student, the dataset reports 34 features in addition to the graduation outcome. It includes demographic data, socioeconomic factors, and academic performance data, which give key information about each student prior to enrolling in college, as well as information on courses and grades in college. Additionally, the dataset reports macroeconomic indicators, including unemployment rate, inflation rate, and GDP from the region. Importantly, this dataset includes a target variable, the graduation outcome, that indicates whether the student graduated, is still enrolled, or dropped out. This is a variable we will try to predict using your demographic, socioeconomic, and educational features. This slide shows a distribution of our target variable, graduation outcome. It is a 3-class classification outcome. It takes 3 values: dropped out, graduated, or enrolled. As the histogram shows, 1,421 students dropped out, 2,209 students graduated, and 794 were still enrolled at the end of the normal duration of the course. Next, we have a slide with a bunch of correlations. I apologize because the slide is a little bit hard to read. A lot of the names might be blurry. But the important thing from this graph is that it shows the graduation outcome is most closely related the number of curricular units in the second and first semesters of this 2-semester course. Next, we look at a broader binary classification approach, which looks at students who dropped out and who did not, whom we refer to as dropout and non-dropout respectively. This histogram shows the distribution of this bivariate outcome. There are 1,421 dropouts and 3,003 non-dropouts. Next, we move to feature optimization. We consider 8 sets of features in order of their correlations with the dropout variable. The objective is to let the data decide which sets of features are most important in predicting dropout. We vary our testing to training ratio. We consider 3 ratios, 0.4 to 0.6, 0.25 to 0.75, and 0.1 to 0.9. We use logistic, decision tree, and random forest to estimate machine learning models with these features and to record the following performance metrics: accuracy, sensitivity, specificity, and AUC-ROC. In the rest of the paper, we will consider the optimized set of features, and we will consider a training to testing ratio of 75 to 25, or 3 to 1, to strike a balance between the training and testing sample. We compare performances of 7 machine learning models optimized using a grid search optimization algorithm. These are cross-validated with 3-fold, 5-fold, and 10-fold cross-validations. The grid search optimized machine learning models that I estimate are logistic regression, decision tree, random forest, artificial neural network, support vector machine, XGBoost, and K-nearest neighbor. Here we present the grid search optimization results. We can see that the grid search optimized random forest model, with these values highlighted in red, performs the best with an accuracy of 0.85, sensitivity of 0.72, specificity of 0.92, precision of 0.82, and AUC-ROC of 0.89. The optimized random forest model suggests that the key predictors of dropout in order of importance are the number of curricular units in the second semester, the number of curricular units in the first semester, and then whether the tuition and fees are up to date. Compare the grid search outcome from a binary classification approach to a multi-class classification approach. The 2-class models were considerably higher performing than the 3-class models. However, the random forest model dominated in both classifications, and the top features of importance, the number of curricular units in the second and first semesters, and whether the tuition and fees were up to date, were the same between both the 2-class and 3-class classification. In conclusion, it is clearly extremely important to develop a model that can optimally predict dropout based on student information. Using a data set of 4,424 students, we compared 7 grid search optimized models and identified what the most important predictors of dropout risk were. We estimated and compared models with binary and multi-class classification, and we found that the random forest model dominated all the other models with 0.85 accuracy, 0.72 sensitivity, 0.92 specificity, 0.82 precision, and AUC-ROC of 0.89. And the key predictors of dropout in the optimal model were, in order of importance, the number of curricular units approved in the second semester, then the number of curricular units approved in the first semester, and lastly, whether the tuition and fees were paid up to date. In order to make this model broadly accessible to the public, we are using the best performing grid search random forest model for developing and launching a web application. With this, students and administrators should be able to input students' data in order to understand dropout probability. Based on these predictions, they can undertake countervailing measures to mitigate dropout risk. Future work that can be performed includes using a larger data set extending across several colleges, collecting additional student information, and utilizing hybrid machine learning models. Thank you for listening to my presentation, and I will open it up to any questions.
Well done, Arko. Thank you so much. I think it's an interesting topic because you yourself and, of course, your fellow panelists are college-bound students. Presumably, our attendees are the parents of college-bound students. So, Arko, I would love to learn why you chose this college-bound, or excuse me, this college dropout category to deep dive into. And did you have any key takeaways that you and your peers can use to your advantage or to share to enhance the college success rate for everyone?
Okay, so the first question you asked was essentially about how I had this idea, essentially. So this idea I've been, throughout my life, or as soon as I first learned about machine learning, I've been, quite interested. You can even say obsessed with it. I found it really interesting how you can take some, random kind of numerical values and feed them to a computer program or a machine learning program, and how it can eventually be able to predict things based on those numbers that you gave it. And since I'm a senior, I started this project a few months ago when I was a junior. And as a junior in high school, colleges are going to be kind of somewhere at the forefront of my mind because I have to worry about applying to colleges and stuff like that soon. So with thinking about colleges and also thinking about machine learning, I I just kind of started thinking about this idea, and the more I thought about it, the more it kind of appealed to me, and the more I determined to take some action on it, do something, and this is what came out of that kind of motivation to do something.
Excellent. Thank you. And do you have any key takeaways for you, your peers, the parents of college-bound students to set themselves up best for success to complete this four-year degree and presumably go on to further education?
Um, well, I would say, I guess the takeaway from this experiment would be kind of the um, I suppose you can use this model in order to kind of you can input your information and see how you are, if your parents are talking about, your parents are probably like not going to college right now if you're probably inputting your students' information, not your own information, but probably inputting your students' information, seeing what the machine says kind of about it. Um, and yeah, that kind of could help. And also using the key factors, I think would help one understand. Um, and I think the key takeaways for students, well, for students is to kind of, I don't know, like kind of be careful about, if the machine obviously can be wrong, but if like there are some factors that might influence that might seem like there's a high risk of dropout in some case, then to maybe be a little bit careful about that. And overall, in general in college, I think a good idea is take tough courses and try to get good grades. Probably a lot easier for me to say that than for it to actually happen, but that's my advice.
That's great advice. And thank you for building this model and sharing it with us so we can keep these different components in mind as folks who work in education, like myself, our college-bound students, and the parents of our college-bound students. So, Arko, well done. Very thorough. Thank you so much for sharing this good work.